distinct pitches arise from the interplay of a fundamental frequency along with an accompanying array of overtones forming a harmonic series. This is because vibrating entities such as strings or columns of air, which emit pitched sounds, do so by resonating not only as a whole but also in halves, thirds, quarters, fifths, and beyond, with each new division generating a harmonic frequency that is a multiple of the fundamental. In a new Python file, we'll import Music21 and within a main function, to be called at the bottom of the script, create a new pitch object called fundamental. Its getHarmonic method can be called to retrieve a specific harmonic above this pitch, denoted by an integer argument. For example, fundamental.getHarmonic7, using a print statement, reveals the seventh harmonic is precisely represented as an F3/4 sharp in the fifth octave raised by an additional 19 cents. To visually represent it, we'll create a note object named seventh harmonic using fundamental.getHarmonic to specify its pitch and invoke seventh harmonic.show. When notated, the pitch is rounded to the nearest quarter tone, discernible as F3/4 sharp. Now suppose that instead of a single pitch, we want to encapsulate a larger portion of the harmonic series, the first 16 harmonics for example. We can do this within a loop. We'll create a variable called harmonic series to which we'll assign a stream.part object. With a for loop, we can use the range function to iterate over a sequence starting at 1 and ending exclusively at 17. Inside this loop, we'll create a new note to represent the ith harmonic, specifying the pitch with fundamental.getHarmonic I, and then append this to our stream. Outside of the loop, harmonic series.show allows us to run the program to view the harmonic series. One potential approach to harness the harmonic series for composition is to derive chords and harmonic sequences from its pitch structure. We'll define a new function called chordFromFundamental. As arguments, it will take a pitch object representing the fundamental pitch and a list of harmonics to be included within the chord. Inside the function, we'll initialize an empty chord object called harmonic chord and then iterate through the list of harmonic numbers with for harmonic in harmonic numbers. During each iteration, a new pitch will be created for the current harmonic number by invoking fundamentalPitch.getHarmonic and supplying it with the harmonic variable. To test this in our main function, we'll create a new myChord variable to which we'll assign the result of calling chordFromFundamental. Using a fundamental pitch of A in the first octave, we'll construct a 6-note chord combining the 5th, 6th, 7th, 9th, 12th, and 15th harmonics. With myChord.show, we can run the program to see it accurately notated. As before, the depiction of the 7th harmonic as F3/4 sharp underscores the potential of the harmonic series to facilitate exploring microtonality. This unlocks intriguing compositional possibilities, but might not always align with our intentions or prove practical. Some instruments prevalent in Western music, such as the piano, are confined to the 12 pitches within the conventional chromatic scale. To account for this, we'll adapt our function by including an option to round pitches to their nearest semitone. We will introduce a third argument called nearest semitone, initialized as a boolean set by default to false. Within the for loop of our function, after creating a pitch for the current harmonic but before adding it to our chord, we'll check whether the nearest semitone option is true with if nearest semitone. Where this condition evaluates as true, we can lever the MIDI property of current pitch. Standard MIDI numbers are integers that correspond to equally tempered pitches. Therefore, current pitch equals currentPitch.MIDI will generate a new pitch object based on the nearest MIDI note to the current pitch, effectively rounding it to the closest semitone. In our main function, when calling chord from fundamental, we'll specify nearest semitone as true. When we run the program, our chord is represented solely by pitches within the chromatic scale, with the 7th harmonic now rounded up to a G natural. Let's now explore how we might utilize the chord from fundamental function to produce an extended sequence of chords. Within specified bounds, each chord will be created with a randomized combination of harmonics and then transposed onto a predefined bass pitch. To achieve this, we'll need to import Python's random module at the top of our script. In main, we'll create an empty stream.part called chord sequence to contain the chords we'll generate, and in another variable, use a list comprehension to create a list of pitch objects to represent a bass line. We'll iterate through bassline with for bass note in bassline. To choose which harmonics should be included within the chord, we'll use random.sample. This function, when given a list or set as its first argument, returns a new list containing randomly selected elements from the original list. Using range to specify a range of harmonic numbers, we'll set the minimum possibility as 4. Since the first 4 harmonics are widely spaced and tend to give too much prominence to the fundamental pitch, and we'll limit the highest possible choice to the 20th harmonic. The second argument determines the number of elements to be selected and therefore the number of pitches within the chord. We'll use random.randrange with upper and lower boundaries of 3 and 6, indicating that the chord may comprise 3, 4, or 5 harmonics. We will create a new chord by employing our chord from fundamental function, providing bass note as the fundamental pitch, and our random harmonics list to specify the harmonic numbers to be included within it. Our next task is to transpose this chord onto our bass note. The interval by which it must be transposed is the same as the interval between the chord's lowest pitch and the bass note. Therefore, we'll create a variable named transposeBy and assign it an interval obtained with a 0 index and the bass note. To transpose our chord, we will invoke its transpose method and designate the transposition level by passing our transposeBy variable as the first argument. To modify the existing chord, instead of generating a new one, we'll set in place to true. We'll assign a duration of 2 or 4 quarter notes to each chord randomly using random.choice, and then append the chord to our sequence. Upon completing the loop, we will invoke chordSequence.show. Executing the program will generate a new chord sequence and open a notated representation of it. Numerous possibilities remain open for developing harmonic material based on this program. For example, we might experiment with altering the number of harmonics within each chord, perhaps gradually increasing or decreasing the harmonic density. We could limit the choice of harmonics more precisely to control the flow of consonance and dissonance. We could also craft more complex harmonies by merging chords generated from 2 or more distinct harmonic series, each rooted on different fundamentals. Let me know in the comments below if you have other ideas for further exploration. I'd also appreciate feedback, thoughts, suggestions, or requests for future topics related to Python, Music21, and creative coding. If you've enjoyed this video, please show your support by liking and subscribing to the channel, and thank you for watching.